I'm also the team leader and the hardware engineer for the project.
Hello, I'm Leslie Palmino, and I major in computer engineering, and I'm the software engineer for this project.
Hi, my name is Henry Figueroa. I'm a computer engineering major, and I'm also taking part in the software development of the project.
And my name is Charlie Restivo. I'm majoring in electrical engineering, and I'm part of the hardware team for this project.
So as for the project motivation, what is the overall view of the project? So what we want is a device that has everything you need as a student within the classroom. So what exactly will it have? It will have a note-taking application that will allow students to open a blank sheet that students can take notes on with a stylus, or open a pre-existing sheet that they can edit for future use. It will also have a file sharing, some sort of file sharing implementation that will also be implemented into it. And it'll also have some sort of test-taking app that we also implemented into it. Who will it benefit from this device? Overall, it would be both the students and the professors. Why the students? It limits their distraction in the classroom from using personal devices such as cell phones, tablets, iPads, etc. And why the professors? It'll ensure the professors that the students are taking part in the class and following along in the lecture. As for the issues being solved, it will solve the issue of distractions that I just previously mentioned, and it will upgrade classroom technology overall.
So our project enables students and teachers to use a new kind of technology in the classroom, while also allowing students to take notes traditionally, at a more affordable cost than other products like the DeskNote. Our project is simple to use. Simply scan your student ID card to unlock your profile. In this time of being more eco-friendly, this product will allow schools to reduce their carbon footprint. The average college student uses 100 sheets of paper per month. So for an institution with 3,500 students like Manhattan College, that's over 1 million sheets of paper per semester. The DeskNote will help eliminate wastefulness by allowing students and teachers to write their notes, but store them electronically.
For the data flow, we have the teacher and student interface. Here we have the interaction between the student and the teacher, allowing the student to import diagrams from the teacher and then import-export their final notes from the note application database. Next, we have the test application interaction, allowing the teacher to import the exams received by the student to begin their exam. Once completed, the exams go back to their teacher as a PDF. That's the overall data flow.
So the theory behind our touchscreen dates back to an American inventor by the name of George Hurst back in 1975. So as we can see from the image on the right, the infrared touchscreen works by using an array of X and white LEDs and their photodetector pairs that are embedded in the bezel around the display. They emit and detect the rows and columns of the infrared light across the face of the display, and the LED beams then cross each other in a vertical and horizontal pattern to help the sensors pick up the exact location of the disturbance, which in our case would be our finger or a stylus.
So as for one of the few software implementations that we put into our project, we decided to implement an open source cloud server called OwnCloud. So what it is it's similar to using a Dropbox and is a suite of client to server software. When originally we decided to implement or use possibly a router when it comes to the file sharing aspect of the project, but due to lack of time, we decided to implement a cloud server. So to access the cloud server, you simply type in into the browser the IP address associated to your Raspberry Pi. Of course, this is also subject to change in that we can also change the actual URL as if we wanted to. This cloud server is actually very easy to use, and logging in is as simple as logging into any other account that you have access to. You can have one or multiple admins added to the OwnCloud. You can have multiple users with associated groups, which I will explain in the following pictures. Our main thing that we wanted was to be able to upload from Windows and have it be viewed in Raspbian in the OS and Raspberry Pi, or vice versa, so that both professors and students can interact using the cloud server. And as for limitations, we would need this software to run on a separate Raspberry Pi and act as as some sort of server, to where all you need to do is just strictly for storage. Another limitation was that it took very long to install, and I also had to account for a dynamic IP and trusted domains, since trying to access the page was very difficult with having the IPs constantly change. So I had to implement a static IP address there. And to explain the pictures, the one on the top I have a PDF file there and also a picture of a circuit that you can see. Hopefully you guys can see. That will be just an example of if a student was to pull a picture that is up there, or a professor is to upload a photo. It's basically like a Dropbox. The picture on the bottom is there's 7 users there. There's a master Capstone admin, we can say, where you have master rights to the cloud server itself. I have 2 professors named there who are different admins for their specific classes, and there are also other users there that are either part of one or both classes.
For the software application implementation, the WinForm application template was used in Visual Studio 2019 using C#. Both the note and test applications allow the student to have only access to the cloud server and are allowed to write and save their work to it as well. However, the test application will have a set time limit of 1 to 2 hours until closure and can only accept exams in PDF format. In the images below, you can see the application's normal CPU usage and memory processing properly through our unit testing.
So in terms for implementing the login or scan-in feature for the project, we needed to create a database, and this is where PHP-MyAdmin comes into play. It was the easiest way we found for someone without any knowledge in coding and SQL to be able to actually create and fill in the database with specific values. So we couldn't just base it off of simply people knowing SQL or SQL when at the end of the day, not everybody might not know it. So to access it, you simply type in your IP address /phpMyAdmin, similar to the cloud server. It implements MySQL to create a database and displays it as well. The same situation arose when it came to the challenges with the dynamic IP. So I had to implement a static IP address so that we were actually able to access the page. And another issue was that there was a lot of outdated source files when downloading the program through Raspberry Pi. And there were errors in Python code, which gave me troubles in actually inputting values into the database. So I also needed to go about and debug that as well. And in the picture above, you can see that there's a screenshot of our database with a couple people in it. You have first name, last name, a student's ID number, address, date of birth, phone number, and an ID card number, which I will explain later. And the one below is the same database, but just run through the terminal in the Raspberry Pi. And here we have on the top right, you can see the scanner, RSC522 scanner that we used, along with the key fob and the ID card. And you can also see the pin, how we connected it to the Raspberry Pi below.
So at the onset of the project, we wanted to remove the screen from the monitor from the casing so that it would fit in the desk better and make the DeskNote look more like other devices on the market. But when we extracted the screen from an older monitor and provided power to it, we noticed it smelled and felt like static, so we knew it was probably dangerous to keep going in that direction. When we looked at the monitor we were going to use for the project, we saw that there was a note that said, "Warning, risk of electric shock, do not open." This was a problem because we knew it would violate safe lab procedures, and it would be an ethical issue because these devices would be put around students and put them at risk for serious injury. So our solution was to create a power bank that would act as a backup power supply. The power bank, this is the schematic, features 4 standard USB ports. We'll be using one of these for the Raspberry Pi. The output is a 150-watt wall port that is capable of outputting 13 to 50 volts. It has a removable battery pack that consists of 15 18650 lithium-ion batteries that can be replaced for extra capacity. These provide about 188 watt-hours of power. The maximum power output should be about 120 watts, and the power bank is about the size of a water bottle. For safety precautions, it includes features that will shut down the power supply in the event of overvoltage, overdischarge, short circuit, over temperature. It also has an automatic cooling system.
So the schematic is broken down to 6 different parts. To the top right, we have the battery pack, and to the top left, we have the charging circuit, and down at the bottom, we have an AC inverter. So how the circuit actually works is that when no power is connected to the power bank, the current will flow from the battery pack through a normally closed contact, the top 2 relays, and then to the inverter output. When power is connected, the current will flow through the charging system to the step-down converter that has constant current, and then it will stop at the 2 relays. At the same time that this is happening, the current will flow through the 2 mini step-down converter, and this will turn on the cooling fan and the 2 relays. And now that the current from the step-down converter with constant current can flow into the batteries. When the output is switched off, this way the batteries are protected from being charged and discharged at the same time. In this part of the schematic, we have a DC step-up converter, a USB over temperature protection circuit, as well as an automatic cooling system. So how this circuit works is that the current from the battery passes through the output and then through 2 normally closed 45-degree thermal switches. The current can then flow into the inverter relay, the boost converter relay, and the USB converter. This is also the over temperature protection system. So if either of the thermal switches detects the temperature of above 45 degrees, no relays can be turned on, so then the power bank shuts off. And this is the automatic cooling system. So the wires for the fan are connected to the temperature switches, which are directly connected to the battery. So the cooling system will always stay active. And over here, we have our PSpice simulation. And here is one output of the PSpice simulation. This is the output voltage of a step-down converter with constant current, which is used to convert the voltage or current source to a desired level. So the turquoise waveform below is the voltage level across the output, where the purple waveform implies the input voltage level. So for a buck converter, which is another name for it, the voltage level of the output should be lower than the input. So given the pandemic, COVID-19, all of our Capstone groups were required to complete their projects while in quarantine. For our hardware team, this meant that we were unable to build the project, so we had to create a simulation for our power bank. This was a problem because we were unsure on how we were going to work on the project together. Charlie and I decided that we would use PSpice because it would be our best option, and we're most familiar with it, as well as we would send files in between each other as we finished the schematic.
And as for the software team, we had less of an effect in terms of working on it. Before the quarantine, the software team was already working independently as it is in our respective parts, so there was no issue there at all. But the issue arose, unfortunately, when we needed to collaborate all of our work together with the hardware team so that we can test everything onto the monitor. In addition, we were limited to working only on one Raspberry Pi when we were working on multiple ones to split the load and to have the cloud server run on its own Raspberry Pi, so it's unfortunate that we could do that. And actually, a couple days ago, one of my HDMI adapters decided to malfunction on me, so I was forced to find a way to remote into my Raspberry Pi, which limited me to actually continuing with the login portion of the project.
For the project completion, both the note and the test application's main functions are complete. We overcame most challenges, and there is still future work for this product if it were to go to the market. C# was a new programming language learned as we programmed each component. For future work, proper integration of the cloud database and notifications are needed for upcoming.
And as of now, the OwnCloud server is set up for file sharing, and it is working with uploading images, Word documents, PDFs, etc. The RFID scanner itself is functional and can read and write data as of now. The database is set up and created through PHPMyAdmin, which is very simple to use, as I had mentioned. And for future work, in the future, we would like to find a direct connection to the RFID scanner, since we're just using PHPMyAdmin simply as a template more than anything. And we also would like to implement maybe a possible attendance system, which we know was already a previous Capstone project, but having that incorporated with our classroom device, we feel as though it would upgrade it a bit more.
So the change mid-course, switching to the power bank, showed us the importance of maintaining safety and ethical codes. For future work, the power bank can be updated to an uninterruptible power supply, and if we were actually going to build a DeskNote, there would be buttons included for saving, switching tools, and scrolling. This change, the quarantine, also brought several new skills to light, since the addition is more involved than our original idea. We developed PSpice skills, learned about 3D printing because the original power bank was going to be in a 3D printed casing, became more proficient in AutoCAD because that's where the 3D files were stored, and we were also given a hands-on way to see how the power supply works.
So this is the breakdown on the bill. Our project cost is to the bottom right, and to the left, we have the total cost per classroom, which would be 30 desks. Although it may seem expensive and over our Capstone budget, it is significantly less for other brands that sell their desk at about $3,000, which would cost $90,000 per classroom, and ours would only cost about $12,000 per classroom.
So this is a demo video of me using the LCD screen overlay to write on the screen.
Sorry, I don't know what happened to the video.
Here's a Note application uploading the image from the Fire Explorer. Then we have the deletion of a drawing along with the point size and color selection, along with the eraser button usage. And finally, we have the save feature and closure of the application.
And here to the video to our left, I am running a command to where I am I'm inputting my name into one of the ID cards. And I am also using the key fob that also came with this. So I'm also running the same command and inputting Amanda's name into that key fob, assigning it to that ID card essentially. The video to our right is going to display me running a read command where it is reading my name from the ID card and as well as the ID card number that is associated with it. And it is also doing the same thing for Amanda with the actual key fob.
So due to lack of time, I'm just going to briefly go over our project timeline. This is the 40% no-go milestone, which we reached last semester. This is basically what we did over the winter break. This is what we did over the spring semester. And finally, these would be our testing results, although we weren't able to have a full integration test.
So as engineers, we're held to the codes and standards provided by the IEEE. Some of the specific standards we used were the IEEE 1008-1987 and the IEEE 26702-2007 standards. And so ethically, there are several aspects to this project that we had to keep in mind. For the student, the DeskNote should not prove to be a method by which they can plagiarize or be dishonest academically. And our method to keep this at a minimum was to limit the amount of internet interaction the DeskNote has. Also, the original hardware design unintentionally poses a safety risk to the user, so we needed to find a way to add a hardware component and to replace the hazardous previous component, which was resolved by the addition of the power bank. These are our references.
And are there any questions?
Okay, thank you guys. Thanks for the presentation.
I'd like to just say thank you to Professor Sultan, the electrical, the computer engineering department, the students, and whoever else is here for letting us explain our Capstone project.
Yes, thank you.
Thank you.
Very good work, guys. Very good. Okay, my compliments.
Thank you.
Very good study.
Thank you, Professor.
Thank you.
Okay, so I'll introduce our